Good day, colleagues. Welcome to this masterclass in electroplating and metal finishing. This course is designed for professionals who aim to master the theoretical and practical frameworks governing surface engineering. We will cover principles of electrodeposition, bath formulation, surface preparation, and advanced finishing techniques. Our goal is to build a scientifically rigorous and industrially applicable foundation for all facets of metal finishing. My program comprises 11 modules. We begin with the fundamentals of electrode kinetics and Faradaic processes, followed by surface conditioning techniques such as polishing, cleaning, and pickling. We then explore plating bath design and control, both for single metal and alloy systems. The latter half addresses chemical finishes, electrolysis and physical vapor deposition, anodic treatments, coating evaluation, and concludes with a module on the economic and regulatory aspects of finishing operations. First module, Basic Electroplating Principles. Electroplating is governed by electrochemical reduction at the cathode, where metal ions are deposited from an aqueous electrolyte under controlled current or potential. The mass of the deposited metal correlates directly with Faraday's laws of electrolysis, where I is current, T is time, m the molar mass, and the number of electrons transferred, and F Faraday's constant. Control of current density, metal ion concentration, and organic additives is critical to tailoring grain morphology, internal stress, and brightness. Second module, Surface Preparation, Polishing and Buffing. Mechanical preparation prior to plating is indispensable for adhesion and defect minimization. Polishing removes macroscale surface damage, while buffing, typically with alumina or rouge, produces a microfinish conducive to uniform nucleation during plating. Improper surface prep often results in gas entrapment, pitting, or adhesion failure. Tooling selection, pressure control, and sequence standardization must be adjusted per substrate, be it steel, copper, aluminum, or die-cast zinc. Third module, Cleaning and Pickling. Surface contamination, oils, oxides, and particulates must be systematically removed. This is achieved through sequential cleaning processes. Solvent degreasing. Alkaline soap cleaning. Electrocleaning, anodic or cathodic. Acid pickling using sulfuric or hydrochloric acids. Pickling not only removes oxides but also activates the substrate electrochemically, promoting nucleation during deposition. Critical here is managing dwell time and acid concentration to prevent substrate overetching or hydrogen embrittlement, particularly in high-strength steels. Fourth module, Plating Bath Control and Process Chemistry. A stable plating bath requires rigorous control over multiple interdependent variables. Metal ion concentration affects deposition rate and morphology. Temperature alters kinetics, stress profile, and grain structure. Agitation minimizes diffusion layer thickness and improves throwing power. pH determines metal speciation and complexation stability. Organic additives, such as levelers, brighteners, and suppressors, modulate the cathodic polarization behavior. Analytical techniques like titration, UV-vis spectroscopy, and cyclic voltammetry are employed to monitor bath integrity and ensure process reproducibility. Fifth module, Plating Baths, Types and DIY Formulation. Common bath systems include sulfate for copper, Watts baths for nickel, chloride for tin, and cyanide for precious and base metals. Alloy plating, e.g., Enesian, SNPB, CUSN, requires precise control of complexing agents and electrochemical parameters due to differing reduction potentials. In DIY or small-scale R&D contexts, bath formulation involves dissolving analytical-grade salts in deionized water, adjusting pH, and incorporating proprietary additives or surfactants. Quality assurance includes testing via X-ray fluorescence, XRF, for thickness, Hall cell panels for bath behavior, and stress tests using spiral contractometers. Sixth module, Chemical Finishes and Conversion Coatings. Post-plating treatments such as chromating and phosphating are essential for corrosion resistance and adhesion promotion. Chromates produce a passive oxide layer through redox conversion, while phosphate treatments form crystalline zinc or manganese phosphates. Lacquering and electrocoating apply protective organic films over metallic surfaces. The latter utilizes electrophoretic deposition for complex geometries. These processes are governed by interfacial electrochemistry, surface energy, and film porosity, all of which impact long-term durability. 7th module, Electrolysis and Vapor Deposition Techniques. Electrolysis plating leverages controlled redox reactions, typically with hypophosphite or borohydride reducers, to deposit metals like Ni or Cu. Unlike electrolytic plating, it yields highly uniform coatings on non-conductive or recessed areas. Vacuum techniques such as PVD and CVD operate in subatmospheric environments to deposit ultrapure metal or ceramic films, critical in semiconductor and aerospace applications. Pretreatment for nonconductors involves etching, sensitization, and catalytic seeding using noble metal activators. 8th module, Anodic Processes. Electropolishing removes surface asperities through anodic dissolution, typically in a viscous acid mixture like phosphoric sulfuric. Anodizing, particularly on aluminum, forms a controlled oxide layer, which can be dyed or sealed for decorative and protective applications. Electrochemical machining and grinding use anodic current in conjunction with tool geometry to precisely shape metals. These techniques rely on electrolyte conductivity, oxide solubility, and pulse current modulation. 9th module, Testing and Quality Assurance. Deposit integrity is validated through physical and electrochemical testing. Thickness, XRF, coulometry. Adhesion, tape test, bend test, thermal cycling. Corrosion resistance, salt spray, ASTM B117, humidity chambers, electrochemical impedance spectroscopy. Process control includes statistical analysis, SPC charts, and failure mode assessment. Specification compliance ensures alignment with standards such as ASTM, ISO, or customer-specific criteria. 10th module, Special Techniques and Business Considerations. Advanced methods like brush plating, pulse plating, composite co-deposition, and jet plating provide functionality beyond traditional tank-based processes. From a business standpoint, success depends on throughput optimization, energy efficiency, environmental compliance, and technical differentiation. Skilled personnel, well-documented procedures, and customer-focused R&D are central to maintaining competitiveness in the global finishing market. In conclusion, this master class synthesizes fundamental theory, applied chemistry, and industrial practice in surface finishing. Whether you're scaling production, troubleshooting deposition defects, or optimizing for cost and performance, this course provides the advanced knowledge required to lead in the field of electrochemical surface engineering. Thank you, and let's begin with next lesson, the basic principles of electroplating. If you like and want to follow, please click subscribe and like and follow.